Waiting for the screen. Yay! Hello, everyone. Music. That was the intro theme for the structure and interpretation of computer programs, which is the course taught at MIT on Lisp. So, computers, what are they even? Nobody knows. My name is Igor. I'm a person from the internet, and the history of Lisp is pretty much a history of programming. So let's start there, maybe. We're the first ever program written by Lady Ada Lovelace in the 1800s for this theoretical mechanical computing engine called the analytical engine, which was inspired by the loom. And then there was, in the 1900s, this guy called Alonzo Church. And he really liked computers, except they didn't exist yet, so he had to invent them. And so he wrote this paper in which he discovered the same thing that Alan Turing also discovered, which is the unsolvability, or rather the undecidability, of the halting problem. And similarly to Turing, one of the things that he came up with in order to actually prove this was a formalization of computation, a way of describing what computers do, of describing the essence of what an algorithm actually is. And so he invented this thing called the lambda calculus, which is a functional programming language that only has functions and nothing else. And then at some point, we got real computers, and people started working on them and writing programs using assembly language. And then there was this guy in the 1950s and 60s called John McCarthy. And he also really liked computers, but he didn't like programming in assembly language because it's this very low-level way, thank you, very low-level way of describing these problems. And he was trying to do something very high-level, which is artificial intelligence. And so in order to be able to do that, he invented this thing called Lisp. Oh yeah, and another thing, he was kind of sick of playing against himself, so he wanted to write really smart computer programs so that he could, because he was tired of always winning. So that was another big motivation. And so he also wrote a very influential paper, probably one of the most important papers in the history of computers and programming languages, titled Recursive Functions of Symbolic Expressions and Their Computation by Machine, Part 1. And in this paper, he describes this system called Lisp, which stands for list processor. So it's a language based around lists. And it was just radically more high level than all of the other stuff before it, because at that point, everyone was sort of working in assembly language or having more low-level languages that then compile down to assembly language. And a lot of really important ideas came from this paper, one of them being garbage collection. He tried to do this Lisp thing, and then he had this issue of resources being used, and he came up with a way to reclaim them, so that's where that came from. So this is kind of where our journey begins. And the examples that I will be showing you today are written in Clojure, which is a Lisp. It is a very modern Lisp. So it's a language in the family of the Lisp languages, and probably the modern Lisp, which is to say that even though a lot of these ideas are from the 1960s, it's still practical today, and you can even use it. Another very important thing, there's going to be a lot of parentheses, and parentheses are hugs. So just keep that in mind. So I will now proceed to teach you how to read Lisp code in one very easy step. So you're probably used to seeing code that looks something like this, where you have some, what is this? It's a function call, and it takes 2 arguments. And this is true in pretty much any programming language ever. Well, not in Lisp. So the way this works in Lisp is, wait for it, like this. So the only thing you need to do is take the right paren after the function name and move it to the left and delete the commas. And that's it. So, yeah? All good? All on the same page? All right. And so one example of a function call would be this, which is calling a function which has the name plus and passing in 2 arguments. And so it's true for Lisp that a lot of things that we have as built-in language features, that we have as built-in operators, are actually just functions. And so plus is just a function that takes n arguments and adds them together. And in a way, it just makes sense. And it keeps the core language so much smaller by simply having those things defined in userland, or definable as functions, as userland functions. OK, and this is what that would return. So, good. So let's grow a Lisp from the ground up and just sort of see how far we can go and sort of derive it from first principles. So what we're going to start out with are these things, which are atoms. And they're just sort of symbols or identifiers that represent some piece of information. And they're undividable. That's why they're called atoms. And so you take these atoms, and then you take another kind of structure, which is this. And this is what is known as a cons cell. And a cons cell is just a structure that points to 2 things. So it's like a pair in that it points to 2 things. And so these pointers can point to atoms, or they can point to other cons cells. Straightforward enough. So the first cell is called first, and the second cell is called rest, and it will make sense in just a bit. And so here's an example. It's just a cons cell that points to 2 values, a and b, which are both atoms. And the way that you could write this in Lisp is a dot b. So that's, when you do this, the in-memory structure would look like this. You can also leave them empty. So you could do a with an empty second thing, and that would be a dot nil. And you can chain these things. So not only can cons cells point to atoms, but they can also point to other cons cells. And when you do that, you can build any kind of data structure that you like. And so this is an example of a linked list. And the way that you would implement a list, a dynamically growing list in, say, C, is exactly like this, using exactly this kind of structure. So it's the same concept. And so this way, you can build lists, and kind of looks like this. But this is sort of cumbersome, right? Because you've got this a dot, b dot, and then like after the 3rd dot, you're already sort of getting tired of it. So there's a nicer way of writing it, which is just this. So you leave out the dots, and you get this nice high-level representation of lists. OK. Now, once you have lists, you can also do lists of lists. And here's an example of that. And, well, a different way of looking at lists of lists is by thinking of them as trees. And so here's a tree representation of that same thing. And if I just go back here for a second, you can kind of see that, right? It's a list containing 3 elements. The first one is a symbol, and the other 2 are lists. And you sort of see that reflected there. Now, if you take a look at this piece of code for a minute, this is code in, say, PHP or JavaScript, and you can read this. You can see, well, it's a function call to a function named foo, and it takes 2 arguments. The first one is another function called toBar. The second one is a function called toBars with an argument cooks. Okay, not complicated. But if you were to take this code and give it to a parser, and if you actually run this code and you have an interpreter or maybe a compiler, then a part of that interpreter or of that compiler would be a parser that sort of reads in the code and parses it into a tree structure. And so what you will get from this is, whoa, that went too fast, is an abstract syntax tree. And an abstract syntax tree is a representation of the code in terms of an in-memory tree structure. And so this is what it looks like, and you can sort of see how that's reflected. So you have a function called foo, and then it has 2 arguments. So sure enough, we have a function and 2 arguments, and it sort of cascades down. Now, if you were to take this syntax tree and try and serialize that down to a list of lists, then you would end up with this. And this is exactly the same list of lists that I showed you before. So this is actually the Lisp code representing the same call as this. Does that make sense? So what this really means is that when you're programming in Lisp, there's sort of 2 different ways in which you can interpret any piece of Lisp code. You could look at it at the syntactic level, at which point you say, well, it's a list of lists, yeah, sure. Or if you want to actually know what is the meaning of this thing, then you look at it at the semantic level. And in that case, you will say, oh, well, this is a function call to a function named foo, and so on and so forth. So you kind of had these 2 levels, and yeah, so here you can see those are 2 functions. So we've got lists, and we've got code that is being represented by lists. And we've got these 2 levels of interpreting that code. The problem is, how do we actually get a data structure into the language? And while you could invent a new sort of syntactic structure to represent data structures in the language, you don't need to, because there's this thing called quote. And quote just takes any sort of expression, and instead of interpreting that expression as code, it interprets it as data. And so the idea here is really that you reuse the same sort of data structure for the code and for the data. It's kind of the same thing. And this is a nicer way of doing quotes, so you can just put a quote mark in front of it. Okay, so now we have data structures inside of the language, and that means we can start doing some basic operations on that data structure, such as calling functions on it, and a function that we could call on it is this function first, which just gives us the first element, in this case, the quoted symbol A. And the way that this works in terms of data structures is really just by following that arrow. So it's a very simple operation, and it's also very simple to implement this. And you can do the same thing with rest, and it gives you the rest of the list, BC, and it also just follows the arrow. And you can also create new lists or add elements to lists using this cons thing, which is just a matter of creating a new cons cell and sort of tacking that onto the front of the list. So now we've got sort of the basic operations going, and we can just sort of add different types of values. So we can add numbers and strings and all of this stuff. But there's one key ingredient that's still missing, the most important one actually, which is functions, because I mean, how are we going to define our behavior in this language if we don't have functions? And so this is how you define a function. And this is one of the very few special keywords in the language. So as I mentioned, things like plus are just functions. And this fn thing is one of the few special ones. And so it just says, well, it's a function. It takes some number of arguments, in this case just one argument named x, and the function body is just x. And that's an implicit return, which you might know from CoffeeScript, if you've ever used that. So basically, the last thing happening inside of the function body is just sort of returned. And so if we introduce variables, and yeah, if we introduce variables, then we can do named functions. So here's sort of the basic hello world function that you can do. And what's worth noting here is that there's not sort of a privileged namespace in which the functions reside, but instead it's shared with the variables. And this is very similar to JavaScript. So in JavaScript, if you define a named function, it's really just an anonymous function assigned to a local variable in the scope that it's been defined in. And the same thing is true for many Lisps, including Clojure. So you just do define value equals function. Okay, and so we can call this function, and it returns a string with a concatenation of hello plus Laracon. All right, so now I want to introduce something that is kind of strange about Lisp, and that takes quite a while to sort of get used to in the beginning because it's just so weird. So Lisp has no loops. And this seems rather odd, but it's actually not entirely true. It has loops, but not in the way that we're used to them. So it doesn't have for each loops or for loops or while loops. What it has instead is, recursive functions. So in case you don't know what recursion is, it's recursion. But really, it's just a function that calls itself in the function body. So it's a function that somehow refers to itself, and that's a way in which you can sort of do looping. And so I want to show you a rather basic example of how you can implement some sort of looping using recursion. So this is a function called member, and it checks if a value x is a member of a collection. So it's basically just a linear search through a list. And so one interesting innovation that Lisp has is this thing called conditional expressions. So this cond thing is a conditional expression, which is a way of writing sort of nested or writing ifs and else ifs in a really concise way. So instead of doing if, else if, else if, else if, else if, you just have the conditions on one side, and then you have the actual things that happen if those conditions are true on the other side. So in this case, we have a condition that checks, well, is the collection empty? And then we have the code that is executed if that condition is true, which in this case is just returning false. And then we have sort of the alternate case. And so if we want to search through a list, there's really three cases we need to consider. The first one is, well, we have a list, but it's empty. What's going to happen in that case? Well, we just return false because you can't find anything in an empty list. Then there's the other case in which you're looking at the first element, and you want to see if the first element is the thing you're looking for. And if yes, then you take it. Otherwise, you want to recur. And so this is right here where the recursive call happens. And what's worth noting, though, is that the recursive call calls rest on the collection, which means it cuts off the first element and recurs on a subset of the original collection. And so if we run through a call real quick, then we have this call to member, and we want to see, is C in the list A, B, C, D? Which you can probably already answer, but let's just go through it to sort of get a feeling of how it operates, because I think this really helps to understand how recursion works and sort of understand the flow of execution. So we have our stack here, which has just one call right now, and the call says, well, is C a member of that? Okay. So let's go into the code. And so we hit the conditional expression, and the first check we do is the collection empty? And it's not, because it's ABCD. So we go to the next one and see, well, is the first element of the collection equal to the thing we're looking for? And, well, A is not equal to C, so no, it's not. Which means we go into this other branch, which recurs. And so this recursive call will take the A out of the collection and sort of restart the whole process. Now, it's worth noting it won't remove the A from the list itself, but rather create a new list in which that value is removed. So this idea of immutability and not changing values in place is a very strong one in Lisp. Probably one of the most important things in general. And so we go to this next call and we check that one, and that one is not true. So we go and check is C equal to B, and it's not. And so we recur again, and now I've got the third call on the stack. And now we check, is it empty? No, it's still not empty. Is C equals to C? Yes, it is. And so now this call returns true, and the truthiness, or maybe just the truth, propagates all the way up the stack. So this is true, which means the thing is true. So yay, we found something. All right. Any questions about recursive functions? Some questions? Can we do questions? All right, let's do questions. No. I'll repeat it.
In your example, you say a new list is being generated. Does
Yeah.
this mean it's separate in your memory as well? Or
So,
a linked list, does it?
yeah. So the question is, I said that in this example, every time you do a recursive call, or when you call rest on this list, a new list is being generated, and is this list, is it actually creating a new list in memory or not? And this sort of depends a little bit on the implementation. But in most cases, if you have a list implementation that is strictly immutable and cannot ever change, then it's safe to just sort of return the subset of that structure in memory, which means you don't have to copy the entire list. You don't have to create a new list in memory, but you can just sort of return, you can increase the pointer and return that pointer instead. So yeah, that's definitely possible. All right, anyone else? Yes, one?
What happens if there is no more rest?
If there is no element in the list?
Yeah,
so,
no more
so
element.
what does rest on an empty list
Okay,
return?
empty, yeah, okay.
It's probably going to raise an error. So you need to make sure that, like, that's sort of also why the empty check happens first. So this empty check prevents the other branch from ever executing if the list is empty. So that's kind of the reason for that. All right, I think we're going to move on then. So macros. I'm going to sort of move on to a slightly different topic now, sort of a bit more advanced things. So macros. Macros are a feature that is not very common in programming languages. I think it originated in Lisp, and it remains to be one of the most common things that you find in Lisps. So let's take a look at this thing again that I've already showed you before. So what is this? Like, what is this even? Is this a list? Is this a tree? Is it a list of lists? Is it code? Is it a function being called? Or like, what is this even? And the answer is, it's really all of those things, depending on how you look at it. Because in Lisp, all your code is data. And if you think about that, well, what can you do with data? You can manipulate it. You can generate it. You can generate data. You can sort of make decisions based on it. So data is very flexible. And if code is data, then we can do all the things we do with data with code as well. So it means we can generate code. We can manipulate code. And that's exactly what macros are about. So if you take an interpreter, then it usually is divided into two distinct phases. You have the compilation phase, and even if it's not a compiled language, I'm going to refer to that as compile time, where you take the string that is the input, you run it through a parser or a reader, and you get the abstract syntax tree. So this step is going to happen in pretty much any interpreter, right? And so once you have that thing in memory, you then give it to the runtime environment, which takes the abstract syntax tree and the environment and sort of tries to run it and evaluate it and make sense of it. And then at some point, maybe if you're lucky, you get a result. But what if we zoom in on this compile time thing, what if we made the compile time extensible? So at that point, when you've got the AST, the abstract syntax tree, in memory, what if you could then sort of mess with that and change it? And that's what a macro does. So a macro is nothing else than an abstract syntax tree transformation. It takes a subset of your code represented as a tree and transforms it into something else. And what you want to transform it into is up to you, because it's exposed to the users of the language. So you don't have to be a compiler writer. You don't have to learn C code to be able to do this. You can just implement this as a function inside of Lisp itself. So you have the Lisp code rewriting parts of itself, rewriting parts of itself to sort of become something else. And so this way, you can implement language features without changing the language and without changing the interpreter. And one example of this is a thing called defen. So defen is just a macro that expands out into define something of function. So it's just a way of shortening this sort of definition process here by generating that code. And what that means is that these things that are language features, that are built into the language, don't actually have to be defined inside of the interpreter, which reduces the amount of special things you need to implement. So in this case, you only need to implement def, and you need to implement fn, but you don't have to implement defen. So it kind of reduces the amount of stuff you need. So here's a really awesome example of what you can do with macros. Now, if you've ever done any functional programming, maybe, or if you've ever even just tried to use functions in PHP, one of the annoying things is that reading functional code often involves sort of reading it inside out. Because a function calls, like if we look at this down here, the function call, you kind of need to first evaluate this thing, and then go there, and then go there, and then go there. So it's very inside-outy, and you can't sort of linearly scan the code, which is one of the reasons why so-called object-oriented wrappers are kind of nice, because you can just do like arrow this, arrow that, arrow do stuff, and it sort of reads more linearly. But if you have macros, you can implement this kind of thing, which is in Clojure. It's called the threading operator. It's not got anything to do with operating system threads, but rather with how the function calls are threaded through, if you will. So you just use this operator and you say, well, I have this list foo bar bars, then I reverse it, then I take the first element, then I take the name, and then I reverse it again, which is a convoluted example, but it just transforms into this other thing, which is really cool. So what would it mean to have macros in PHP? Because this is a PHP conference after all, so we might as well think about what we could do with these ideas, right? And I think there are a lot of annoying things in PHP. Many of them are very small, but they kind of add up as well. And I feel like there's a lot of stuff that if we had macros, we could sort of alleviate the pain a little bit. And one of them is defining constructor arguments and just defining properties in general. Because you need to write the same word 4 times just to define a thing. I mean, come on. So we could have a new syntax that looks something like this, and you just put the arguments there, and it expands out into the more verbose and more annoying notation. And by doing more of these kind of things, and by decreasing verbosity, I think we can also sort of save a lot of the mental overhead that programmers encounter every single day, because you need to sort of scan through the code and there's a lot of noise there. And by reducing the stuff that you're looking at, I think you can sort of save a little bit on cognitive resources. But I think this idea is a lot deeper than just adding cool little things. I think this it could change the way that PHP itself works, or that any language itself works. Because if we can add new stuff to the language, then we could also, any new feature that has been added to PHP in the last few years, if we could have added that using something like this, added it as a library instead of adding it to the interpreter itself, then we could have saved so much time. So, for example, if you take the current version of PHP, which is HHVM, they have this nice thing called short array, not short array syntax, but short lambda syntax, short anonymous function syntax, which is really nice. It's just so short and concise. I love it. And so if we were able to take this and translate it into the old stuff that's annoying, then we could get all the nice features. And what this really means is that we could keep going with this and backport all of the features from every single PHP version to every previous version. And so you could run the code that is running now on HHVM, you could run that on any old PHP version, and you wouldn't have to wait for PHP internals to fight it out. You wouldn't have to wait for all of the hosting companies to upgrade. You wouldn't have to wait for your team to decide, or your sysadmins to decide that they finally want to upgrade to the latest version of PHP. And more importantly, you would have the power to add these features yourself, which can be a dangerous power to have, as the history of Lisp has shown. I mean, it does sort of, it results in a lot of competition and means more arguing in some cases. But I think it's a very powerful thing to have, and you know, just think about what that could mean for all of us. Okay, so I've talked a lot about how to make a Lisp and how, what kind of useful ideas we could take from Lisp. And now I just want to show you some of the really sort of amazing stuff and mind-blowing stuff that has been done in Lisp, and it's sort of a bit more computer sciencey. So computer science. It's not really a science. It's more like engineering or art, maybe. And also, it's not so much about computers. It's, let's face it, it's pretty much magic. So there's this thing called the Y Combinator. Not that stupid company, but like an actual concept called the Y Combinator. Not Hacker News, but the actual Y Combinator. And this is the Y Combinator, and I'm just going to first explain what it is, and then I'm going to explain what it is. So it's a function that takes a consumer function, then defines an inline function that as an argument takes a function, then calls that function on itself, and then takes that inline defined function and calls it with an argument. What is the argument? It's a function that takes a function, and then calls the consumer function with the argument function called on itself. That's the Y Combinator. So what does it do? It's pretty straightforward. So the Y Combinator is a way of describing recursion without referring to names, without having explicitly named variables. So it's a way of doing recursion just by using anonymous functions. And it's a very beautiful concept in a way, and it's not really useful, but it's definitely mind-bending, and I think it's interesting in the sense that we can take an existing language and start removing stuff from it and see how far we can get, see what kind of stuff we can continue to do in that language even with those features removed. So if we remove named variables, what would happen? Well, the Y Combinator sort of gives us a way to work around that. So here's just a quick example of actually using the Y Combinator. First of all, we define this factorial function because that's the only thing programming is useful for. And so this takes an argument f, then defines the sort of factorial thing that you generally are used to, if you've ever seen any factorial thing. And so this f, while it's an argument, will then refer to the function itself that is being returned. And so what you can do is you can call y of factorial, and then call that returns you the recursive version of that function, and then you can actually call that with a value. And so this is kind of pointless right now because it's using named variables. Like I'm using y and factorial, which I just defined as named variables before. So what's the point here? Well, you can take the definitions of those two functions, and so you can just inline them. And now it's no longer using any variables whatsoever. And so you can call that, and it works. And it gives you, what, 125? Maybe. Anyways, so that's quite a cool and mind-bending kind of thing. OK, now I want to show you something slightly different. So what if we removed numbers from a language? Could we still do something with it? Could we maybe represent those numbers in a slightly different way? And Alonzo Church, in the Lambda calculus, already kind of came up with a way to do that, which is Church numerals. So Church numerals are a way of representing numbers in terms of functions. And so a Church numeral is a function that takes a function, you guessed it, and calls that function n amount of times. So 0 is just a function that takes a function and never calls it. 1 is a function that takes a function and just calls it once. And so just to show you an example of this, this is a way in which you can convert a Church numeral to an actual number. So you just call it with inc, which is a function that increases the value. So you want to call inc n amount of times, and you start with 0. So if you start with 0 and then you increase it, increment it n amount of times, you're going to get the actual number. And so if we try this with the Church numeral for 0, then we can see what happens. So we call this thing, identity on inc, that returns the identity. Identity is just the function that returns whatever value you give it. So identity of 0 is 0. Okay, so that works. And so we can try it with 1, give it inc. So f of inc returns inc, and inc of 0 is 1. And you can do it with 2, so this sort of becomes inc of value, and so that returns 2. So you can see how this works, right? And so this means we don't need variables, we don't need any of those numbers, and as a matter of fact, we can pretty much represent any kind of data structure or any kind of algorithm using only functions. And that was the core insight of the lambda calculus itself, because it's such a concise way of describing computers. So it's basically, it's the functional equivalent of a Turing machine. And you can also define all these operations on church numerals in terms of functions. So you can do like increasing inside of the church numeral space. Okay, but that was quite simple. So let's look at something a bit more. Yes, you may. It's fine, I'll repeat it.
Isn't this like very memory inefficient?
Okay, the question is, isn't it very memory inefficient? And the answer is, it depends. So if you were to implement this in PHP or most languages, probably yes. In general, probably yes, it's going to be memory inefficient. But there's certain optimizations that you can do in functional languages that sort of prevent that from being an issue. One of them being tail recursion, where if you have a function call at the very end of a function, usually you would add sort of a stack frame and then you like keep incrementing, sort of increasing the stack size, and at some point you get the stack overflow. With tail calls, instead of increasing the calls, it sort of stays on the same level and does a jump instead of going through the stack. So that's a way of saving memory, and it's a technique that can be quite effective for not having those memory issues. So I hope that answers the question. Yes? I still keep the 0? You mean here? So this is really just a way of translating from the structure, like from the function version, into an actual value in the language. But you can omit that. So you can use, instead of using like this inc operation, you can just use those things. And then what you get back is not an actual number, but it's the church numeral of that number. So you get this function that's probably going to look like garbage, and then you need to somehow figure out what number that is actually representing. So yeah, you don't, if you restrict yourself to only using functions, at some point you're going to have to look at the function you got and figure out what it's going to do. So yeah, that is sort of an issue. All right, cool. So, crazy stuff. A metacircular evaluator is an interpreter written in the language itself. So, an interpreter that sort of is able to interpret itself. And so here's an example. This is a Lisp interpreter written in Lisp. And John McCarthy actually presented this in his 1960 paper. So it's fairly short, as you can see, which is really amazing. This amazes me every time I see it. It's like, can't be true, can't be true, no way.
We have the same thing.
We'll get there. Yeah, but I think this is really cool because it sort of shows how the fact that Lisp uses the data structures or uses the same data structures for code and data and makes those somewhat interchangeable, it's really at a sweet spot for doing exactly this kind of stuff because you don't need to do the parsing because parsing tends to be quite a complex task. And so I think that is one of the reasons why it's possible to sort of cut it down in size. So yeah, 62 lines of code. It's pretty good. So what would it take to write a Lisp interpreter in PHP? So here's one that I did. It's also pretty short, which maybe shouldn't be that impressive now that you've seen the other one. So it's not exactly a transliteration, but you can definitely, if you sort of tilt your head a bit, you can see the similarities there. But that's not the question that you've all been waiting for. The question that you wanted to know the answer to is, how much code does it take to write PHP in PHP? And here's the answer, about 6,000 lines of code. So Anthony actually did this. He wrote a PHP interpreter inside of PHP. And this is not a complete implementation, but it implements a fairly decent subset. Now, it's worth noting, though, that doing the parsing also adds another 6,000 lines of code. So yes, that's a lot of code. And it's just an amazing accomplishment as well. All right, and I think that sort of brings us to the end of this presentation. A few things. So if you're interested in this kind of stuff, I've got a few books that you can check out. I recommend this to most people I meet, The Little Schema. It's a really good introduction to Scheme and the possibilities that it brings and some, like the simplicity. I think it's a very nice and inspiring book. There's also this one. I've not read it, but I've heard good things about it. It's about doing game programming with Lisp. There's the structure and interpretation of computer programs, which many people regard as a Bible of programming, and it is also a pretty fat book, and I haven't read it, but I've seen parts of it, and it seems to be really good, but also kind of tough. And finally, if you want to get more into sort of something more practical, then I can really recommend this one, which is focused more on sort of the modern way of coding and using closure and integrating with a JVM and that kind of stuff. So yeah, that's that. And that's it. Thank you. Question?
Yes, I read the little schemer, totally digging it, and then right after I read it, I forgot how continuations work. So would you mind explaining that?
Continuations. Oh. So there's a sequel to the little schema called the seasoned schema, which has this thing called continuations, and they're basically a way of. This is really tough. They're a way of capturing the current context and turning it into a function, and you can then use that function, and when you call it, you sort of can go back in time. So it's a bit like a goto that is lexically scoped and captures the entire environment of where it was defined. And so you can use that to implement a lot of things like exceptions without having to have exceptions. So yeah, I don't know if that probably doesn't do the concept justice, but that's the best I can do for now. Cool. Next. Come on. Come on. Questions? No one?
That's kind of sad.
There's one.
All right. considering all the stuff that's possible with macros and stuff, how maintainable does your code become with that sort of thing available? Like I can only imagine what PHP people in WordPress and stuff would do with MySQL query in views and stuff if this sort of thing was available to them. Like, do you have any thoughts on that?
I don't think maintainability is that much of an issue in general, because once you've written a macro and it's written in a robust way, you can just sort of leave it there and let it do its thing. And I don't think you really need to change it that much after the fact. I would agree that it's quite hard to debug macros, simply because they're generating code, and like there's sort of some disconnect between the code that you're reading and the actual code that is running in the end. So that's definitely a challenge. But I think, well, with great power comes great responsibility.
Yeah, I have a question. So being a Laravel conference, just to bring it back to some relevance for everybody, can you do facades and static methods and things like that in Lisp? We love facades. Oh, I mean, static all the things, right?
So static method really is just a function, so yes.
Damn. When jokes backfire, huh?
But there is a strong emphasis on statelessness, and so one of the things you can do in static methods or in static classes, if you will, is hold state and change that state. And I actually have a slide for this because I totally saw it coming. I'd say the PHP community has been going very strongly into this sort of object-oriented mindset during the last few years, and functions have been somewhat neglected in a way. And so I feel like we should maybe consider going back to that at least a little bit and think about some of the functional ideas as well. One of them being statelessness, because that is something that almost no one in the PHP community talks about. Like, what's with all the state? Come on. There's some discussions about value objects and such, so there's a little bit of that, but I think it's sort of evaded the mainstream of discourse, and I'd like to see more of that. So yeah, that's also one of the reasons why I'm doing this talk, to sort of bring some of those ideas out there. Anyone else?
Are there any particular industries, domains, or problem spaces that you see Clojure and other Lisps being particularly used and useful in relative to other types of languages?
It's a general purpose programming language. As such, you can use it for anything. I'd say something interesting that I have seen is some of the stuff that's in Clojure makes it very good for concurrent programming, and that's one of the benefits you get from immutability as well. And so there was someone who wrote a database in Clojure, which is not something that I would want to do in PHP, to be honest. So you have the tools to do that kind of stuff, but I think it's viable for websites as well. Yeah. Go ahead.
So regarding the web world, so if you're using Clojure and maybe a framework like Noir, right? How do you see that fitting? Like, how good of a fit would that be for the kinds of applications that many of us might be making, or how relevant is it to really what we're doing? Is it a really dramatically different kind of solution that really suggests that we should have, I don't know how to say, different kinds of outcomes in order to pick, like PHP or Clojure with like kind of like the web support system that they have?
It's hard to tell because I haven't really done any web development with Clojure, mostly just messing around. So I don't think I'm really qualified to answer that question. Yeah, I don't think I have a good answer, sorry.
Any more questions? Well, thanks so much, Igor.
Thanks.